Okay, so continuing with the bacteria colonies that we were looking at, previously these were two independent populations. And now we haven't changed the differential equation for y, so we still have dy dt is minus 2y. And that differential equation we've already solved. We already found that that solution was given by y is equal to, say, some constant c2 e to the minus 2t. But the differential equation for x has changed. So before we just had dx dt was 3x, but now we're adding this 10y on over here. And if we're assuming x and y are populations of bacteria colonies, then x and y are at least bigger than or equal to 0. So having a differential equation like this, adding this 10y term on, y being positive, means the presence of y in colony 1 actually is going to make the rate of change of x be even bigger. So that means the presence of y in colony 1 is actually making that bacteria colony grow even more rapidly. So it's almost like that's a catalyst that's making the population X grow even faster. So we do have some interaction. The presence of y is making X grow faster. However, X has no effect on the rate of change of colony Y. So we have different interactions here. So our solution should represent that. Our solution for x should somehow be tied into the solution for y. So in part B, we're asked to come up with an educated guess for the form of the solution for x of t, and then go ahead and try and find it. So here we're going to take a similar approach to what we looked at when we worked with second order system with constant coefficients, where we were kind of guessing a particular solution and then finding the values of the undetermined coefficients in that particular solution. So we have dx dt. I'll just write this as x prime is equal to 3x plus 10y. And now let me just replace the y with this. And so we saw previously that this term over here led us to believe that our solution should have something like a e to the 3t. And now, because the derivative of x is also involves some e to the minus 2t term, then it makes sense that we might have another part of that solution for x which involves an e to the minus 2t. So here would be like my guess for a particular solution for x. And now we can check this solution by plugging it back into the differential equation. So we would have x prime of this solution, which would be 3a e to the 3t. And then I would take the derivative of the second term there, and I would get minus 2b times e to the minus 2t. So what we want is x prime should equal 3x plus 10y. So now I've got my x prime, which is 3a e to the 3t minus 2b e to the minus 2t, and that should equal 3 times x. So I'm going to multiply 3 times my original guess. And then we're going to add to that plus 10y, where we knew that y was c2 e to the minus 2t. And then just like we did previously, we can now group our terms and match up the coefficients. So I've got one term of e to the 3t. I've got one term of e to the 3t. So what I see from this is that a is arbitrary, which is good because if we're finding a general solution, then we should have some arbitrary constants in our solution. And then we can match up all of the e to the minus 2t terms. So that's the remaining 3 terms. And so from that, we can see on the left side, I have minus 2b. And on the right side, we have a 3b and a 10c2 plus 10c2. So solving for b, because that was our undetermined coefficient, we get that b is actually equal to minus 2 times c2. So that gives me altogether, plugging these values back into my original solution, my guess at least, we found that a was arbitrary, and now we found that b was minus 2c2. So here's my solution for x, and here's my solution for y. And so now we've solved this system, and we do see that there's some relationship between these two, because I'm seeing this constant c2 in both of those solutions. But what we're getting now for our solutions are some linear combinations of exponential functions.